Chen Pauli, and Pauli is also my supervisor for my master's degree. So, so actually, it's been a while. So anyway, I'm very happy to give a talk here again. Actually, I'm giving talk in this place once per while, so it's kind of interesting to still talk about something new. In fact, today I'm going to talk about something more technical compared to the talk I usually give. So hope it's okay for you. So from the title, you see that we're going to talk about jet and the substructure. Something sounds a little bit strange or find kind of funny, but I'm going to tell you what we are going to talk about. The first thing is that, as mentioned, CMS is actually associated with the collider at LGC. So first, LGC still the largest particle collider built by human beings so far, right? Still, and it's still colliding billions of protons per day, almost about every second actually. So colliding a lot of things, not colliding a bicycle, but colliding particles. So in a collision, well, although this plus looks fancy, but in fact, if the protons are accelerated to a high energy and collide at collide at high speed, so many interaction things actually happens, and interesting things can be produced, including a special object which we call jet. So you say, what is jet? Well, ideally, or I'm not sure this is the same for everybody, but once you hear jet, maybe this is something you can think of. Yeah. So if you really collide the protons and come up with a jet like this, it can be very, very interesting. But I doubt it will happen. So what we are going to talk about today is more like things like this, not this kind of jet, but something like this. In fact, this plot, this data is collected from Atlas. It's from another experiment, but I find this plot is very nice to demonstrate what a jet means. So, for example, this is a typical so-called dijet event from a proton-proton collision. What do you see here? There's a lot of things in the middle that a little bit the tilted curves. Basically, that means that they are charged particles. And the things hit this is something like towers type things. That's actually the kilometer hits. So that means a jet in the particle collision means a lot of energy, a lot of particle, and they produce a cone-like structure thing, just like this. Okay? So this is a very typical dijet event. And then we come back to particle physics. So what kind of things actually can become jets or jetty particles? If you look at the big table of single model particle, in normal way, what we say is that usually all the light quark or gluon can become a jet in the detector. So that means a typical 5 quarks like U, D, CS, and button, or a gluon, they can usually become a jet in the detector, and they become not just like single particle that produce a lot of particle and a lot of energy. And we can measure them together in a cone-like structure. And not just quarks or gluon, even a tau can still decay hadronically. In general, we can also identify them as a jet because they produce plenty of particle, also not as high activity as other jets, they are usually said. But not more than just like a single quark or single gluon. If you have things that actually can decay, for example, like a W or Z, two-thirds of WZ actually decays to 2 quark. So in this case, and that can become like hadronic events, so they become actually produce jets. But these 2 jets can be like close to each other because if the momentum of Z or W is high. And also other things like top quark can also decay to 3 objects, which usually decays to like W and B, and the W also decay to 2 quarks in about like 66%. So that means a top can be also treated as 3 jets. And even further, the main decay of a Higgs boson, which was only discovered a couple of years ago, can have a very high chance to decay to 2 quarks or 2 gluons, and eventually become 2 jets, right? So that means that if we are colliding protons and produce all these so-called small particles at the collider, and we do have a high chance to see a lot of jets. Okay? So this is basically the key point at the why people have to spend a lot of effort to study jets at the collider. So let me show you a big idea like this. So if we come back to a more technical way of saying sensing, so if you learn this particle physics or like quantum field theory, in general, a quark or gluon or a parton is just like a quark line, right? And in your diagram, but in reality, in jet or a jet in the detector, it becomes like a jetty things in the detector. So a jet can be something look like this. You see a lot of charged particles, a lot of neutral particles, and a lot of electromagnetic shower, a lot of hadronic shower all together. So this is a way for us to identify, okay, you see something like this, it becomes a jet. Or then we can say, okay, this jet can be a quark or gluon or anything else. Okay? So this is a general field, but this is a jet. But today I'm not just going to talk about jet, because today jet is more standard. We want to talk something just about a structure, because if you can see here, there's a lot of particles, right? So they are not just come out with uniform, they have some way to produce a particle. So we can even study the structure of the things hidden in the jet. So, so this is the idea. So actually, it only takes several years. So people study a lot of this so-called jet substructure, and try to do reconstruction, and try implement and deploy in many physics studies actually. And the key idea is like this. Just I just showed a little bit earlier that so what we see is a jet in the detector, but it can be not just a jet. It can be even like a heavier particle, like it can be a W, a Z, a top, or Higgs, or light quark, or gluon, or button, or Chen, or even just from background from high up. So there are many tools have been developed during the past few years. So today I basically more or less want to summarize what happens on the development during past 2 years or 3 years. And one interesting thing is that you may find all these algorithms or tools all have a very fancy names somehow. So you're looking into it a little bit more. So anyway, so the first thing is like the typical physics case is like this. So you can imagine something like this. Those particles not so heavy. WZ Higgs is like 100 GeV level, and top is like 170 GeV. But we are colliding protons at TeV scale. So that means all these particles can have a relatively good chance to get a very high momentum. So high momentum means the separation angle between the decay daughters are small, right? So for example, just like you have a very high energy particle decayed by you, they are not separate from each other. So that means if the energy is low, for example, like here a soft or low momentum W will decay to 2 quarks with a wide angle. So you are basically seeing 2 jets. And when momentum goes high, these 2 jets become merged. So you see only 1 jet. But since this is a jet, it's formed by 2 quarks. So that means one can actually study the structure of this the decay particles or the jet substructure things. Then you can actually identify this is a W, not from a regular jet. Similar things also happen for top. Top is also even more interesting because top actually decays to 2 things. Right, first it decays to W and B. When the momentum is high enough but not super high, the W can merge between 1 jet and you have another 1 B jet. But if the momentum goes even higher, everything merges. So we get the 3 jets merged into 1. So it becomes a kind of strange things, but people can still find a way to identify there are 3 things hidden in a single jet cone. So this is what or what people usually do to take this is a top jet. So I'm going to show you one event. It's a typical CMS event, but they're very interesting because they actually have only 2 jets. But these 2 jets basically look like 2 tops. If people can calculate the inferred mass of these 2 jets, they're all around like 170 GeV, very close to top mass. And people write it through the particle inside, you see those particles actually have a smaller cluster than considered with like 3 jets hidden in a big jet. So this is a very nice demonstration of the quote-unquote boosted top pair events collected by CMS. So this is a way, so-called, we have to define how do we take or how do we identify those kind of particles at high energy collision. So today I'm basically going to talk about how do we do this. Okay, not just showing a event. I tell you so, but there must be a way, right? But since this is something like heavily depends on how we actually measure particles, so we still have to introduce a CMS detector a little bit. So not too much, but just tell you how we detect particles. So this is CMS detector. Well, it's a big one, actually. Well, not the biggest one in the world, but it's pretty big. This is a single human being, so this is your size. So it's only like 5 floors tall. So not as tall as our building here, but it's still pretty big one. And the typical way of detecting particles is something like this. This is a small GIF animation. So you can see, in fact, CMS detector is kind of a so-called classical detector. Mostly, also the material is not so classical, using a lot of silicon detectors. But the idea is just like this. We have different parts of detector detecting different things. So in fact, our detector is designed to measure not too many different things. We only measure muons, electrons, or charged hadrons, or neutral hadrons, or photons, and nothing else. So this is kind of funny, right? You build a huge thing, but in fact you cannot detect everything, not just something like this. But the way what we do is basically try to identify a particle by particle. For example, for muon, we have a so-called charge track, because it have a charge, so it's curved in the magnetic field, and since it's muon, so it does not have carbon energy left in the ECAL, and have another track at the outside of the detector in the muon chamber. And for electron, it's doing similar things, but they have a track inside, but will die in the calorimeter, and generate a lot of shower in the ECAL. And also for another two types of things, for example, like a charged hadron means cation, pion, proton. They do have a track because they have a charge, and they will die in the hadron calorimeter. And also neutral hadrons, well, the neutral things have no tracking, so that will not leave the track inside the detector, but they will die in the calorimeter as well, just like a photon, but they will die in a different place. And the jet, our main character today, or actor today, basically is concept like light quark or gluons in general, means that we have to combine a lot of information from all those particles and try to see if they form a cone-like structure or not. Okay? So this is the basic idea. So in order to proceed, I need to tell you how CMS will construct a jet. So the basic idea is like this. So in fact, there are many so-called jet algorithms developed in past like 20 years-ish. So in general, it's like you get a lot of so-called measurement from detector, and you try to group them into a cluster-like thing. Like you find a cone, put everything in, you measure the form momentum. This is a typical way. But in CMS, the people are doing something slightly different. What we call is so-called particle flow algorithm. It's a little bit different from typical so classical way of jet detection. In old days, what people do is like, okay, we see a cluster, like in the calorimeter, we add a cluster together. Usually it depends on the calorimeter very much. And the CMS is doing something different by combine the information from different detectors and make each particle by particle, as I just mentioned earlier, all these particles generate signatures. And what we can do is to actually pick up one particle by particle by combining the information from different detectors and get the best possible measurement, and use this measurable particle to make a jet. So this is what we usually call particle flow algorithm, and this kind of jets used by these so-called particle flow objects become so-called PF jets. This is what the jargon we are using. So just let me show you a little bit more how the particle flow algorithm was designed. The idea is like this. Classical way people doing measurement is that okay, you have particle fly into a detector. So you have a track, such in curvature, and you see energy left in the ECAL. There's an electromagnetic calorimeter and a hadron calorimeter, right? So this is a typical way. So in old days, people do reconstruction based on those information directly. But nowadays, at least CMS is doing something different. Okay, let's cluster things first. This is a so-called classical way. But after that, try to link those cluster back to the track, or try to connect things together. For example, you see there's a track here, or you see an ECAL here, ECAL cluster here. You say, okay, this one must be from a thing, and this guy also from a thing, right? That's two different particles, and they all hit together on this so-called HCAL cluster. So what people do is actually, okay, this one looks like maybe two things coming from here. Maybe this is partially come from this particle or partially from that particle, and actually can try to cut the energy by half and try to separate them in a different way. And or there's a leftover energy can try assign. There's a neutral hadron here. Try to get all the information there. So that means try to count one particle by particle. So in the end, we actually see the whole picture like they are charged hadrons, they are electrons, they are neutral hadrons or photons. So it's become very effective actually. Well, one thing is that simply because generally CMS HCAL has the modest resolution, so this is the one way for us to recover the whole detector performance. But in the end, they become very powerful. So nowadays, I think most of all the analysis in CMS is using this way, so-called particle flow algorithm, and now there's an even fancier name called so-called global event description. So it means that you try to look through the whole detector, try to group things according to their property, and say, okay, one particle by particle. Okay. So
excuse me.
Yeah.
So for instance, now you have this momentum information from a track.
Yes.
And also the energy information from your calorimeters. Then you say because they hit at the same points.
Yes.
Yeah. So eventually, when you combine all the momentum or energy of the particles, right? Then you should choose just either the information from the tracks or the energy, but you cannot use both.
Yeah, it's basically there's some kind of ordering based on which usually tracker based on the resolution, right? Tracker have the best resolution, so information come from tracker first. If we cannot separate and try to use the information from ECAL, if it's still not working, use the information on HCAL. It totally depends on the detector resolution. So it's kind of the ordering algorithm that depends on the detector property. So it's a way to try to really recover the energy one by one and the higher granularity in this way. Okay.
But what happens is that you have so many tracks, heat.
Yeah, and it become very difficult. In fact, I'm going to show a little bit something like how we improve this at the run to there's some way to do this. Yeah, I can point a few words on how we separate the particles in this kind of case. Anyway, so let me continue. So somehow this is a bit too bright, but anyway. So I just want to say the reason why the particle flow algorithm improve the whole reconstruction is simply because, just like I mentioned earlier, because our tracker have a very good resolution. It's a fully silicon detector, so that gives us a best resolution so far. And our ECAL is good, but our HCAL have like 120% error. So by combine everything together, we can actually pin down the uncertainty of the whole jet measurement, become like some reasonable scale, and it can be very give a very good performance in terms of only the resolution and the direction. So this is a typical idea, and about this improvement, what we can still do for nowadays. So it's still too bright. It's okay. So recently, people are trying to do something like this. For example, you can imagine that when there are many particles go together within a jet, and they all overlapping with each other, right? So the way is that people can try to add more so-called tracking step when the track actually within the jet. So this is a way so-called jet cone tracking, and also there's some other way of so-called pixel cluster splitting, when you can see when the track are hitting together on a single pixel. Then how do we do? So this is one way try to split the cluster into two, and one associated to one track go to the other one. So there's some kind of more fancier way of doing the tracking. And the similar idea can also do for the photons and also other neutrons. For example, this plot shows a very classical. This left-hand side was the classical way. For example, when the big cluster here, like three parts, basically what we call basically a big cluster. So you have a HCAL cluster plus two ECAL cluster. But in the newer way is that since we know this ECAL have a finer granularity, basically have a smaller crystal. So, for example, we can actually separate the HCAL cluster according to what we measure in ECAL. Separate this energy become two. Now this one will become two hadrons instead of one. and there will be 2 photons. So in old days, we'll see this like 2 particles. Nowadays, we can split the energy around their shape and ecal and become like 4 particles in fact. So in the end, well, it's a bit difficult to see here, but this just want to show the improvement between old algorithm and new algorithm, and we see a sharper method resolution by comparing the information. So this is basically a typical idea, okay? So let me move on. But something I still need to mention, the reason why we still want to try to improve all these things is simply because we want to face a critical challenge, means something like a pi-r. Pi-r means something like this. Actually, when people colliding, or when we are colliding these bunches of protons, it's not just one particle hit by another particle. It's basically impossible. It's like a bunch of particles hit the other one. So the number of interactions per bunch closing is not 1. It's actually a big number. Nowadays it can be 50. In the near future it can be 100 or 150. So it's like a big number. So that means people can see this kind of things. Each yellow dot here means 1 collision. So one event is like this. So everything is like put together, and we get a lot of multiple interaction in a single photo, a single event. But this is a way for us to getting higher luminosity. So we have to work a way to pick out the right one. For example, okay, this one have a muon here, so this one is the one of a concern, and we want to throw away all the other stuff. So basically, this is one have to find a way to pick out the right event out of, or right collision out of this big event of many collisions. And this gives us a higher luminosity, but we also need to work on it. So this is basically the price to pay. So nevertheless, this is what we compare the 3 experiments. CMS Atlas basically have higher luminosity, but we have to face this kind of issue. So the idea is like this. So a raw event basically looks like a jungle. In fact, everything is like put up together, a lot of different trees. So the way what we are trying to do is try to cut out all those trees, kind of grooming, and become a nice garden, right? Something like this. So this is a typical idea. So how do we convert this big jungle to become a nice garden? Oh, well, we'll talk about this. So before we move on, we need to understand what is pi-r, or how they behave. They are basically just like a nominal soft QCD events, or so-called minimal bias interaction. So basically we have several handles. One handle is that the pi-r event or pi-r interaction is like more or less random, uniformly distributed throughout the whole detector. So one way we can actually do is try to majorly average activity throughout the whole detector and make a subtraction. Just like you subtract your pedestal or noise, right? So this is a typical way by calculate the average activity of the event and cut it out. For example, this is the pi-r, but this is a price is that this is assuming pi-r is always uniform, but it's not true, right? It actually have some distribution, so it's not very good, but it's working at some extent. Another one is that just like we mentioned earlier, there are multiple interactions, and our tracking actually can find the so-called interaction point, right? So what we can do is like we just pick out the right one and using the vertex information to throw away the others. So this is basically working very well, but the problem is that this is only working for charged particles. For neutral particles, basically there's no way. So in typical way we are doing is actually we calculate charged particle and throw away the neutral particle, assuming neutral particles and charged particles they have a similar so-called relationship or similar fractions. So it's a kind of assumption. But anyway, it's working but not totally good. Another way is so-called using so-called topological events information. For example, just like I mentioned earlier, like if this jet is formed by a W decay to 2 jet and then merged together. So this jet must have a 2 so-called kind of structure. We can cut out the unnecessary thing. And in this case, this is a way to kick out some of this pi-r. So nowadays, CMS is using a new method, or well, it's not very new, already a couple of years, but it's called a very cute name called PUPPY. This is so-called PUPPY approach. So this is a kind of called a pi-r per particle identification. But anyway, PUPPY is easier to remember, just like a cute one, right? So the idea is like this. Since CMS is using so-called particle flow, so we have many particles here, particle there. So what we can do is actually we can calculate the probability of each particle to be piled up or not, right? So based on all the information we have, like how if they are uniformly distributed or not, depends on the tracking information, depends on the nearby activities, all other things. Then can put them together and become a kind of probability. So the idea is just like we can actually count the probability for each particle and throw either away or not depends on this value. So that's the way to do. So people already show already so-called demonstrate the performance on this kind of new algorithm. Actually give us a very good resolution improvement on the missing energy, especially when the pile goes high. Well, it's a bit difficult to see, but anyway, just say okay when number of interactions is high and it becomes very stable, and also decreases in the background by like 25%. So it's a very good algorithm. And a few more things like it should also improve the jet mass resolution. You see there are many particles, and then you throw away the right one, the resolution eventually becomes narrower, and also it becomes very more or less stable. In old method, this so-called CHS was a so-called charge hadron subtraction. This is an old method based on the vertex information, and they will make the so-called the measure of the mass actually have some dependency on the higher up. But after using this per particle way of a calculation, it becomes more or less flat. So this is also a very good improvement that you will get everything more stable along a different pi up or different interactions.
So this is in this algorithm. Do you use a neural network?
It's not yet. It's not yet. Yeah.
Oh, just
basically more like likelihood based.
Likelihood.
Yeah. So let me continue. So this is how we treated the pi up, and then we can come back to how do we deal with jet substructure, the main topic today. So the key idea is this: now we have a jet. So we want to know what's the origin of this jet. It can be a quark, can be a gluon, can be a WZ, Higgs, top, anything, right? Or something we never know. So basically we can think of some so-called key variables, try to identify which one is the information. So one key information is the jet mass, because you can see the spread of particle. If they are heavier, you get a wider spread. If they are lighter, they are more concentrated to each other. So basically, jet mass is one of the important variable. And in order to get a good jet mass, we usually need to do some grooming. Grooming means that you cut out unnecessary stuff. For example, you cut out those okay, it's working. Yeah, some so-called unwanted cluster, and that can be improved with so-called so-called jet mass resolution. There are several algorithms usually called trimming, pruning, subdrop. Those kind of things will help us to identify the mass of the part of this jet. Another one is so-called as additional algorithm depends on the property itself. There's a way usually this kind of usually depends on how many so-called substructure or something. So how many subjects are within a big jet cone. For example, like top, you may expect there will be 3 things merged together. So basically, we can count how many things actually inside the cone. So one typical variable is called so-called n-subjectness. It's designed to count how many subjects within a jet. And then there are a few other things actually are also discussing. So first thing, let me talk about grooming. Well, just like try to make a haircut for your dog, or puppy. So there are 3 different algorithms nowadays people are using. One is called trimming. Well, I'm not going to go through the details. Just like basically they are all doing similar things by cut out unnecessary particle within a jet cone. So there are 3 different things. One is called trimming, pruning, or soft drop. Nowadays, soft drop is probably the most popular one. So basically, you can see they are doing similar things. They have different good or bad benefit. I'm not going to talk about details, probably too much here. Anyway, so once we have this kind of information, then we can get a proper so-called proper jet mass, right? So what we can do is so let me just show you one slide to summarize how we study the jet structure within CMS. I mean, the whole in the instrument. So first thing, what we do is like we get the so-called PF candidate, means using running this so-called particle flow algorithm to get all the particle information measured. So you get the 4-factor, you get the vertex information. And the second is apply so